processing, you're dealing with pockets or ensembles of photons and individual particle type thing. And it's a much different thing. Frankly, I haven't had a formal course in quantum electrodynamics. This is Richard Feynman made that name very famous. But whenever you're dealing with photons, when you talk about there's a frequency, there's a polarization, there's two other things. Some are virtual and some are actual real photons. And I gotta just say this, just so you know some perspective on it. If you think about a magnetic field that's caused by current flowing in an inductor at a constant, just a DC current, those photons around there are called virtual photons. They're not propagated. They're there. They're resident. They become real if you short that thing. Suppose you put a resistor across it, and the field collapses. Now they can become real. Some of it can be launched. Same with the capacitor. If you charge a capacitor, the electric field about the capacitor is static, is made up of an ensemble of virtual photons, not real. There's a difference, and the virtual have different properties.
You're just talking about metaphysics at this point. You're not talking about anything real.
No, this is absolutely you can measure this. There's nothing unknown about this. It's measurable. It's not a metastate. It's not measurable.
Is it observable?
Yeah, absolutely. Photons are the most observable of the small particles, and there's so many experiments.
Has anyone ever seen a photon?
It's just like an electron. Your eyes can't grasp that. You know they're there by the effect they have on things. And we absolutely know photons are there, electrons are there, things that we term this. Now the thing about virtual photons and some of these other states where the photon per se is not moving is that they are in a reference frame and they're, I call frozen in space. They're not moving. When I think of a photon, the photon is moving, if you know what I mean. It's moving at the speed of light. Virtual photons aren't. They're just resident right there. That's at least my thoughts on it. But when you get into things where they get into very low signal level laser type maser or radars, when you're talking about little super small pockets of energy in quantized states, that's when it's well out of my realm. I've never dealt with anything like that. But there are people that are doing it. And how many people are missing, Tom? We're missing 3 people.
He might be doing co-op interviews. Andrew's in town.
4 people, right?
I think 2, but I don't.
Tom's not here.
Yeah. No, Chase.
Yeah.
All right. Well, you don't think they're coming?
No, well,
All right. Well, anyway, what I wanted to do today, we're into chapter 14. I covered basic Fourier transform and then the DTFT from that. I gotta get my map. All right. I'm going to start here. I'm going to mention Nyquist theorem and the reasons it's important. And also, what I'm going to tell you, I'm going to try to keep the material, the way I lecture about these things like DTFT, DFT, FFT, Z-transform, I'm going to keep consistent with what you used in signals and systems. He has different notations, so I want to make sure about that. First, let's just go through why Nyquist is so important. And I think we all know it, but for consistency. Can you guys shut the back door? Let me shut this back door, please. When we talk about the Nyquist theorem, what it boils down to is how fast you have to sample a signal in order to be able to completely recreate it without aliasing. And this is one of the standard things done. So they're going to say, first of all, I'm going to have some signal x of t. It may look like this. It doesn't matter really what it looks like. And it has a transform that looks like this, where this will be omega b minus omega b. Now you can see the spread here is 2 omega b, and I'll stay in the omega domain. This is x of omega, and it is the signal. This is a standard type of thing that they do. You have, call it the magnitude, you have some function, you take the transform of it into Fourier domain, you get this. By the way, when I say x of omega, I mean it's equal to the integral from minus infinity to plus infinity of x of t e to the minus j omega t dt. That's, we're not gonna use the 2 pi f. I mean, we can, but I like to stick with omega because that's what you've seen over and over again. When we go ahead and take this signal, x of t, and we sample it, or we multiply it by delta of t minus nts, where n goes from minus infinity to infinity. And here ts is the sampling really, it's a sampling time step. And f of s is equal to 1 over ts, and omega s is 2 pi over ts, or it's 2 pi fs. The only thing I'm doing is making sure we're clear that that ts has to do with the sampling rate. Well, when I do that, and I call this x sample of t, and I look at the spectrum, now we've done this a few times, who knows what the next step is if I want to look at the spectrum if I have x of t times that, do you remember? There's one straight step here before we go to Fourier. What do we do with this? We turn it into anybody? Exponential series, right? That was the whole key to that. We went and we said that really x of s, just follow me on the steps, that way with some of the stuff coming up, you'll at least be thinking that way. I'm gonna say that it's really x of t times the summation of 1 over t times e to the minus j and omega sample t from n equals minus infinity to infinity. Y'all remember doing that? We turned it in, the bed of nails into that, and that doesn't look like anything that makes sense to me. It just doesn't. By the way, you can write this series as a summation of signs too, if you want to. For every e to the minus j and omega st, there's an cosine of n omega st. There's a cosine. There's an e to the plus j n omega st on the negative series. You can turn it into a cosine series, but it doesn't do anything for you. So if I have this, now I can say something real clear. I can say, I have, pulling this in here, I have the summation of, and I'll put the 1 over t here, of x of t times e to the minus j n omega st, from n goes to minus infinity to infinity. And now, and that's x of st. Now when we go to the frequency domain, what happens? Do you remember? There's one transform property you have to remember. What happens if I have x of t and I know it goes to x of omega? What happens when I have x of t times e to the, in this case, minus j n omega st? It goes to horizontal shift, right? It's going to be shifted by that, but this one, if it's a minus j, it shifts it with a plus sign. So this becomes x of omega, and this would be plus n omega s, right, over t. And therefore, when I take the Fourier transform of that, this entire series, each term in here ends up being shifted. The x of omega is shifted. So the transform of this becomes really the summation. We'll put the 1 over t out here, and it's going to be x of omega, either plus or minus. I can do a plus of n omega s right here, from n equals minus infinity to infinity. I'm going to mention one other thing. He does this in a book, and it's typically done in all the literature I've seen. Normally, when you go into the frequency domain of the transform, you'll change from that, whatever you use in the time domain as the index, to something different. Usually they put k here, or something like k, to indicate they're in a different domain. Now, if you look at this, you know, some of you may be asked this in an interview. I've been asking people what kind of questions they get. I don't know if you're gonna get this, but I'm just saying, I could see this being a reasonable question if you're taking an interview with radar. If this is the actual omega b minus omega b here, that's the original one. Well, we know we get the original when k is 0 and it's scaled by t. But now you get something out here, an omega s, and it's going to be a replica of what's down here. And then you get something out at 2 omega s, and they continue on forever, right? Make sure you remember this with all the, when we do discrete as well as continuous type stuff. Do y'all follow me on this? That's step and repeat, that always spaced by that. Now, what's the minimum distance before this overlaps that? It would be 2 omega b is omega s. And what that means is, when 2 times omega b is that gives us the Nyquist criteria, and that means omega S has to be at least greater than or equal to omega B, or else what happens is these overlap like such. And this is called aliasing, and you see this, by the way, accidentally, not intentionally. When that happens, then you effectively get this. In this area, you have the superposition of two different sets of of the parts of the spectrum. And I want to say what it involves is, does anybody ever listen to say something aliased, sample at a rate, not, say you sample audio, you take an audio signal and you sample it at 500 hertz. And then you recreate the signal by going and taking that through a low-pass filter. Does anybody ever listen to this? It sounds garbled. You hear all sorts of like voices on voices and stuff
It's
like
one
that.
of the DSP projects if you take that class.
Does Reeves do this?
Yeah.
Does he
It's
actually
one of the things you
listen?
have to do.
Yeah.
You
Well,
have to do it in that lab.
Is there a better way? I say it sounds like voices on voices, or it's garbled, but there's actually a way to say that. It's a, what do
It
they
sounds
call
very
it?
underwater.
It's a summation of echoes. Is that another way to say it? Does it sound echoey to you at all when you did it? Did you listen to your own voice, or what did you listen to?
I think it was a clip that he provided.
Normally, it's voice you want to listen to. You want to say it yourself and then listen to it when it's aliased. It's very clear. You can discern it yourself, but you know it's messed up. Aliasing radar is horrible, but it happens. It can happen. That's basically Nyquist. So it means anytime you want to be able to recreate the original X of T, the low frequency signal, you have to sample at twice the highest frequency of interest in that low frequency signal. It's not the highest frequency of interest talking about the carrier. That's not necessary. All right, that's one thing. Now, the next thing we do. I have some things about quantization. He has a lot of stuff in there. I gotta tell you, the real thing with quantization is you worry about the dynamic range and the error introduced. Now, when you took your courses in digital, you probably dealt a lot with quantization error, didn't you?
Yes.
And when you had quantization error in Dr. Tugnay's course on communications, did he talk about the associated quantization noise too or not? No. The radar, this becomes important because there's sources of noise from everything. All right, first, I want to tell you, typically when we talk about signals in radar, and we don't talk about the high frequency actuals. I mean, we don't take a look at the signal centered at a high frequency and the actual spectrum of the Fourier transform of that frequency. We almost always bring it down to baseband. And when it's at baseband and it starts being sampled, the general way to define this X vector will be some X of 0, that would be the first sample, then X of 1, then X of 2, X of n. And in his book, he says it's usually a transpose. Now, the reason he's saying that, the way data processing, and we'll do this in a while, they normally have the first column here would be actually stacked from top to bottom, this would be fast time going down. So this is associated with fast time. Are you with me? Just think about this.
What is fast time?
When you talk about a radar pulse, it's a good question. In general, if we have we'll call this is going to be a coherent processing interval, like this. If there are M pulses, each with T, which is the PRI, right? Then this right here is the coherent processing interval, right? Now, we take a look at this. If we're talking about fast time, we're talking about the return that's associated right here. This is fast time. Think about it, the maximum non-ambiguous range is in here, right? So we send it out. As soon as we stop sending, we're listening from here to here, and then we send again, right? So we gather information in here. Y'all follow this? The air from here to here would be fast time. This is the fast time. Now the next pulse goes out, and we listen. And I'm shooting at the same spot right now, we're not moving. This is just having several different coherent processing intervals in one dwell. Then the next vector would be here, here, and here. Each one of these is associated with a PRI. And that's your data block for the first dwell time. You're gonna have so many coherent processing intervals, and they'll be stacked like this. Do y'all follow me? I mean, there's probably other ways, but this is how most people do it, and I think the book does it that way. Now, round two, now we move in either azimuth or elevation. So now this is where the next dimension comes out. Now we come out of the board here, and we fill in that same block. Then we come out, it's just a visual picture of what you're doing. And you have to store data like this. One other thing I didn't say. Usually, this point here, it doesn't have just magnitude. What it will have is magnitude and phase. There'll be two components to this always. And this is at baseband, not high frequency. And that's how it's stored for future processing. Something else you have to give appreciation for is now this stuff has undergone sampling and quantization, so there's error from quantization. And there's two things that you talk about when you deal with quantization. One is the dynamic range. There's probably a lot of definitions we can say. Dynamic range is always the ratio of the largest possible value that you can measure without any kind of, they call it clipping or anything like that, divided by the smallest possible bit you can resolve. So it's really V max measured over the minimum possible. That's technically the dynamic range. For us, what we have to do is we have to take this total range from V max to V min, and we're going to partition it into 2 to the B levels. Now B is a number. It could be, this could be 1048, it could be 512, it could be anything where you take 2 to the B. You follow me? There's 8-bit, 10-bit, 12-bit, whatever you want. I want to tell you one thing. Obviously, the more levels, the less the quantization error. That should be obvious to you. But the problem with the more levels, there's also more data storage, and then you hit a hard limit where you can't access your data fast enough, even if you can store it. So there's all these trade-offs with that. The dynamic range that you get, if you think about this, V max would be associated with 2 to the B minus 1, V min would be 2 to the 0, so the dynamic range that you would get for a digitally sampled thing would be 2 to the B minus 1, where B is a number of bits. Then he has in his book a formula where he talks about an actual error involved in this, or noise, and this is on page
505?
505, thank you.
SQ&R?
Yeah, and what it's the SQ&R, and it's really a signal to quantization noise. And he doesn't go through a whole lot of detail on this. He gives you a formula where it basically takes the noise power, or the noise power in the signal divided by signal power divided by the actual delta squared, which is going to be the change, or the quantization level squared divided by 12. And I want to make mention of one thing on this. This formula I don't use here. When we talk about error introduced, we're actually going to take the type of signal that we look at and look how quantization affects the actual accuracy in the signal versus the inaccuracy. That's a little bit later. I'm going to try to do that. I want to just mention that really his formula right there, I don't think you got that in communication, but I might be wrong. Do you remember that formula for this signal to quantization noise?
It might have been in that form, but we did cover that.
Normally they talk about the level of fidelity, or how much disinformation or inaccuracy you add. But he puts that in terms of a noise power. All right, now the discrete Fourier transform I was working working on it last time, I want to just tell you a few things, because we're gonna use this, and then we're gonna get into the Z transform, and, from Laplace to Z, so we can draw similarities, and then we can do some of the problems. There's a couple errors in the problems. I think it was 3 or 4, the one where it has a signal from 95 to like 125, and they want to sample it and bring it down to baseband. Well, they assume that the signal stopped at 115, not 125, and their center frequency is wrong when they do the sampling of that one. But going through this is a rehash, and I'll tell you what I'm doing in a second. So when we had Fourier transforms, we know that x of omega was equal to the integral from minus infinity to infinity of x of t e to the minus j omega t dt. And we knew the dual of that, x of t, was equal to 1 over 2 pi here, times the integral from minus infinity to infinity of x of omega e to the j omega t d omega. We call that thing a very specific name. That was analysis. We gave it that name because it's used to analyze a known signal. This is typically termed synthesis, and this is important. Because here, what you think of is if you have a filter response, low pass, high pass, band pass, as an x of omega, this would be the impulse response from that filter. And what's really important to gather is, what did you know, the one thing about impulse response, we didn't create the filter yet, but let me just talk to you about this. Suppose I have a filter, a certain filter, and I know the characteristics that I'd like. Then I take a look as when that filter is hit by an impulse, right? And I take a look at what happens in the time domain. There's a classic example of this. There are certain things that are non-causal that can happen. It means the filter can't be used in real time. Do y'all remember this class? How many had me for signals and systems? You did? Did you? You did, didn't you? No? No? Nobody? Oh boy. You're the only one. Well, then you probably can lead us through this. What do? We say, no, come on, you know this one. Remember this one? I did this with you. I know I did. I said this is going to be my h of omega, my filter. I'm going to have 1 here, just call it omega b minus omega b, all right? Now, if I hit this filter, if this is x of t, here's my filter, h of omega. Remember, and this is going to be my output y of t. If I hit it with delta t here, my output is h of t, correct? This is where we get the finite impulse response idea for finding the h of t and doing fast convolution. Just to give you perspective, I'm not going to do it right now, but just think that in the back of your mind. Now, what happens if I have this as my h of omega? What is my h of t? This is the question. He knows this one, he should at least. We get it by doing what? P tau of t, that's a pulse of height 1 from tau over 2 to tau minus tau over 2. That transforms into the frequency domain as tau times the sinc of omega tau over 2. You all agree with me? That's a direct forward transform. I'm going to use duality to get at the next part. So if I take that, tau times the sinc, now, not omega, but t tau over 2, right? For duality, you take omega and you replace it with t in the time domain. You take the structure or the form of the function there, the mathematical form, and wherever there's omega, you put a t in, you come to here, right? Then when you do this transform this way, you take this function, first you multiply by 2 pi, because I'm keeping it in the omega domain, and then you put p tau, and you replace t with minus omega. Do y'all remember doing this? That's duality. I covered duality in here, didn't I? Everybody? All right, now, what can you tell me about that? Is that an even function, p tau of omega? It's a pulse, right? It's even. That means you can get rid of that. All right? Now I'm going to divide by 2 pi on this side. Please watch this. This is important in some of the work we're going to do. You with me? Now I've got at the transform of my filter. This is my filter here. I said it looks like this. Well, isn't that really p tau? Why don't I make it I'll make this over 2 to make it even easier, all right? So the width will be omega b. Well, what happens here? If I have this as just omega b, then anywhere over here where I have tau becomes omega b, right? I eliminated the need to divide by, or multiply by 2. That's the reason I did it. Follow me, guys? Now, if I hit this thing here, please listen to me, and I hit it with the impulse here, delta of t, and this is time, right? What happens to the output? The output is what? This, right? What does that look like? That's time, right? This is something he loves, because we're just talking, we're talking about non-causal systems, right?
I would say way complicated, but yeah.
Here's what happens. This event that triggered that event is at t equals 0. Do y'all see that? But you'll notice there's information already out at t minus that. Follow me on that, class? That's an impossibility. The net effect is this filter can't be used, can't be built for real-time filtering. It's an impossibility. And we'll get into more of that later. Y'all follow me? Now, the truth is, please hear me. If you have a data record, when I was at Penn State, they have instrumentation and be up in the atmosphere for a long time. Satellite data, or they had other stuff. And they would get long, I call them strip charts of information, where they might have 24 to 48 hours worth of data. Now they have all the data known for all time that would be of consideration. For that particular data set, you can use a filter like this to get information. Y'all follow me on that? Now you can use a bandpass for that, but you can't for any real-time filter, where you're taking real data, getting real output, real data. An event that has not yet happened cannot trigger something in the present domain. Like something that happens 3 years from now can't have an effect on us now. Does that make sense? That's non-causal, and that's something you have to be aware of. With real-time processing, it becomes essential that you understand before you ever start building filters and messing around with things like that, that they are non-causal. I mean, that they are causal, pardon me, not non-causal. And this is a glimpse of non-causality in the time domain. It's the classic example. Do y'all remember this at all? Well, he does, because he's had me. I make a big bit of this. I mean, I really go on about this for a while.
Never learned anything remotely this interesting in signals and systems.
Signals and systems actually is supposed to identify this kind of behavior. It's critical that this comes really, it shouts out at you, because in the real world, I'm telling you, there's engineers out there that do bizarrely crazy things that they should know better, and somehow they either missed that lecture or they just didn't remember anything. I've never seen this done, but I've heard about it. You know how you read 75 ohm cable? Right? Does that have anything to do with a resistance measurement? No, right? 75 ohm is a ratio, right, of L over C, square root of L over C, right? That's what it is. Well, there are people that will take 75 ohm cable, clip it, and think that there are 75 ohms if you short the leads together and you measure it. This is not an exaggeration, but you can see how they could make that mistake. There's all sorts of bizarre behavior in people that should know better. And I can only tell you one thing. Never underestimate this foolishness of some people, especially with live rounds of ammunition, because I've seen it live, up close and personal, when they've literally had a cannon misfire. Instead of hitting a target, it took off part of the top of a sand or of a dirt mound and ended up in a bay because somebody just didn't attend a lecture about how to lock down a cannon. It scares me sometimes. All right, now, that's synthesis, that's actually, this is analysis, this is synthesis. This is the one we're going to do a lot of design work with this one, all right? But it will be in the discrete domain. Now, when we take this, y'all remember how we took that, and when we sampled it, we effectively got this, and this was going to be the equivalent discrete time series, where now we have n equals minus infinity to infinity of x of n times e to the minus j n omega. Correct, class? That's important. That's a very important thing. This is the DTFT. And I'm keeping the actual symbolism that you used when you had signals and systems. Everybody remember? Now, he doesn't do that. He uses an omega prime. But he'll change that. The real thing is this, that when we talk about omega, that's actually equal to omega back here times TS. So you can block that for a second. The relationship between this omega and this omega is that one is multiplied by TS. I mean, the small omega times TS is R omega, all right? Another thing that's important is that a capital omega right here causes, I mean, the signal will repeat itself every 2 pi. By that I mean this. If you have minus pi and plus pi, and this is the omega axis, then if your x of omega magnitude looks like this, then you'll get this. It step and repeats. Every 2 pi. That's real important to know. When you do signal processing, now, there's a lot of crazy stuff that goes on here. This gives us an idea that if we have things that are stepping and repeating all through the axis, if I sample this one out here, I can bring that one out to baseband and stuff like this. It gives you a perspective, but don't worry about this. Our domain that we work in is exclusively from here to here. This is the domain. So we work from minus pi to plus pi when we consider DT-FT transforms, okay? That's important. Let's just do y'all remember the DT-FT, right? And by the way, what's the inverse DT-FT? That's, by the way, analysis. How do we get x of n? Do you remember? It's the same exact form as this, right? 1 over 2 pi. Please try to notice the similarities. This is really important. Same exact form, but now the limits are from minus pi to pi. And now it's x of capital omega times e to the minus j n omega, or capital omega, d omega. You'll notice that this and this one are identical in form except the limits. Look at the limits. That one's from minus pi to pi. This is from minus infinity to plus infinity. This should be a plus. Again, that should be a plus. They're identical. There's one very powerful theorem that comes out of here. Please watch this. Now, if I know, and I hope you got this out of your signals and systems course. Marcus, when did you take that? Signals?
2011.
All right, that's way back in time. You guys are within the last 2 years, right? Everybody else in here is within the last 2 years?
Probably 3 for me.
All right, here's the deal. These sums are ugly to do, and by the way, the inverse sometimes become problematic. I'm just telling you, they're not easy to do. But one thing we do know is the Fourier transform pairs, for most things, are fairly well known, and you understand, for most types of functions, right? So here's the idea. If I have something, if I have an f, or call it an x of omega here, and I want to get the time domain form of this, I want to get x of n. And I go ahead and I look at some of the transform properties, and I'm going to just give you the specific example. If I see my x of omega looks like this, I don't want to make it any more complicated than it needs to be. And it's going to go from omega b over 2 to minus omega b over 2 with a height of 1. And this is in the frequency domain, and this will be my magnitude of x of omega. Now I want x of n here. Are you with me? What I do is this. I look and see if there are any functions that look like this one. Remember, this is from minus pi to pi. Any functions that exist just from minus pi to pi, or really over some closed range of frequencies, but don't exist everywhere in the frequency domain. For instance, I know that if I have this function, that's p of omega b of just omega. Well, I just said that this has a transform of just tau, of omega b, right, over 2 pi, right? Did I erase that one? Times, times the actual, pardon me. I said this was omega b over 2 pi times the sink of omega b times time over 2. Do y'all remember we just did that Fourier transform pair? Do y'all remember that? Now, here's the deal. if I go ahead and I said I have the same thing here, but now I'm in the omega domain, and say I go from omega minus omega naught over 2 to plus omega naught over 2 here, and I have 1, and I wanted to know what the transform of that was. Because I have this in the Fourier domain, look at the definition. That's the Fourier transform. You'll notice the transform limits were only they were between minus pi and pi, not minus infinity and infinity. You all see that? When we integrate that thing at that p of omega, right there, p tau of omega, it's 0 for anything but between minus omega v over 2 and plus omega v over 2. You all see that? So now, really, these limits do occur, and when they occur, the only thing I do is find the x of t that I know and replace t with n. So this would be omega b over 2 pi times the sinc of omega b times n over 2. You follow me? I'm going to go through some more examples where you can get the actual inverse dtft in the time domain by using Fourier transform pairs. And this is real important because DTFTs, if you look at this stuff right here, what we're going to be doing is, this right here, this is going to be our filter property. We're going to do a lot of things where we customize. We're going to take a look at filtering and the effects of windowing in the frequency domain, all sorts of stuff. But what we have to do is have something realizable back here that we can look at as the response to an impulse. That's always the first test of the filter's behavior. You've had digital signal processing, some of you have too? Isn't that, I think Reeves probably says something to that effect, that you always look at the impulse response of the filter first when you're actually taking a look at the overall behavior. I don't know if he does or not, but I think he does, doesn't he? And doesn't he take a look at both phase and magnitude, because you have to have a linear phase ramp if you want non-distortion? I'm sure he talks about that. We're going to go through these issues, because this has to do with how you deal with radar signal processing as well. If you look in the book, he gives you just brief snapshots of this. He's not going to go through the detailed theory and talk about all the important things. That's really continuous time versus discrete time Fourier transform. Both the information, with the integrals, by the way, in the time domain or n domain, the summations in n are over an infinite amount. That's the key in that. Now, if we go through and next look at Laplace transforms, why are Laplace important in general? I mean, we've got Fourier, why do we need Laplace or vice versa? What's the one big benefit of Laplace? There's one thing you can do. The word is design. Laplace transforms, you can do controls work. You can control the design of a filter, of anything you want, very easily, right? So briefly with Laplace transforms, keep that in mind too. Fourier analysis, both DTFT and continuous time, is mainly used to see the spectrum. It's not for design, not mostly. You can, but most of the time, all design stuff is done in the S domain or the Z domain. So when we have a Laplace transform, question, what is it? Well, there's two forms. We use this one. We say x of s is equal to the integral. We start here, start at 0. There are dual-sided or two-sided Laplace transforms that start at minus infinity. In almost all engineering cases, because for design, we start at t equals 0, and we go to infinity. And then we have x of t, e to the minus st dt. Now here, s is equal to sigma plus j omega. Sigma is a real value. It's attenuation coefficient. Omega there is 2 pi f. It's the real frequency in the actual. You could say, if you take this and make sj omega, you get the Fourier transform. If the signal has values that are non-zero only for t equal to or greater than 2. Do you all agree with this? Let's just show the similarity. If x of t equals, it's x of t for t greater than or equal to 0 only, then if we have x of s and replace s with j omega, we have x of omega. We have the Fourier transform.
So you're saying that the attenuation constant is 0.
Mm-hmm.
What does that practically look like in a circuit? Or like, Like, how would you?
The attenuation constants, that coefficient is used when we're taking a look in the S domain for poles and zeros. But when you realize, if you're talking about realizing it with real
Right,
circuits,
because I feel like when we do transient analysis, we use Laplace, and then,
you can, well, Laplace,
like for AC analysis,
what
we
you really
use-
want to do is see, you want to see how it's used, how it's applied to design, I think. The pole zero analysis comes from, I'll just tell you this, Marcus, since you brought it up.
Yeah.
This, do y'all understand how the Fourier transform right here, X Fourier, is the Laplace transform with S is equal to J omega if the function is only valuable, has non-zero values only for t equals 0 greater than 2. Y'all see that? Just plug it in here. Right, it works, it's identical, because if S is J omega, it is the Fourier, right? And this is analysis. But what he's getting at is what's the value in the attenuation coefficient. So if you take a look at this, let's just say I have Sx of S is equal to 2S over S plus 3. All right, 2S over S plus 3. And I do a pole zero constellation. This is the S plane. Now we've had this, and this is the real axis, sigma, and this is the J omega axis. Then how do we show poles and zeros? First, where's the zero? Just take a look at that, anyone.
0,
All right, so you hit this and you put a little zero there, right? Where's the pole?
-3.
It's right here, -3. The standard rule, and a pole looks like this, right? The standard rule is if the poles are in the left-hand plane, it is a stable system, right? If the poles are in the right-hand plane, it's unstable. Let's take a look at an unstable system. Suppose I have X of S is equal to A over S minus 2. What's the inverse Laplace transform of that? You should know this, but I'm on to. In general, what is it? If I have e to the a minus at u of t, that goes to 1 over s plus a, correct? All right. Well, if I have a over s minus 2, the a scales right there. Instead of minus a, I have e to the 2t u of t, right? That would be x of t associated with that x of s, right? What's the problem with that in a simple sense? It's going to infinity, right? All responses that are unbound as time goes to infinity are unstable by definition. So your pole zero, if you're looking for this thing in the S-plane, that tells you if you have a stable or unstable response. If it's unstable, we can make it stable by doing adding some stages, filters, if you will. Everybody okay with that? Good. Now, getting back to the original point here. This is continuous time. The next is, what is x of t if we have x of s? Does anybody remember that one? The fundamental definition. We don't use it, remember? It's 1 over 2 pi j, right? Times an integral from minus infinity to infinity of x of s e to the st ds. We never use that. We always do pole zero. We do really partial fraction expansion of x of s, and we take them back that way. This is applicable, but it's never used. All right? I promise you. You can look in a book. It's there somewhere. We don't use this. What we do is we expand partial fractions and then take them back. Now remember, this is continuous time, but I'm trying to build on what you know. Now, if we have these two things, if we go to discrete time, now if we go to discrete time, we take a look at this. So I'm going to say now my x sample to t is going to be x of t times this bed of nails, n equals minus infinity to infinity of delta of t minus nts, and ts here is the sampling interval. What is the Laplace transform of that? This is how we get the z transform. Please remember this. Well, I'm going to take it into the fundamental definition. I have x of s is equal to an integral from minus infinity to infinity of x of t, that's this, x of t times the summation from n equals minus infinity to infinity of delta of t minus nts, and it's times e to the minus st dt. The only thing I've done there is replaced the x of t in this with the sampled x of t. Got me on that? Now, how do I deal with the next step? Anybody remember? This is classic. This is one of those things that kind of, someday when you're teaching, you're going to be doing what I'm doing here. The one thing you do is interchange the order of operations. You see how both t and n are mutually exclusive of each other? So one thing I do is just say that now what I'm going to do is take the summation out here for n equals minus infinity to infinity. And then I'm going to take the integral inside here. And one other thing before I do this, I want you to just get this with me one more time. You see how I have x of t times this bed of nails, right? The only time this value is non-zero is at NTS, correct, class? So what I do is put NTS there. Now what I do, the integration is with respect to t. I take my x of NTS here. Now I have the summation from n equals minus infinity to infinity of delta of t minus NTS, right? Times e to the minus st dt. Oops, sorry. My bad. The integration should just be there. Integration from minus infinity to infinity. Do you all follow me what I've done? I've changed the order of operation. Integration inside, summation outside. And I prove the x of NTS outside, right? What is this going to be, the integration? When does this delta function turn on? At t equals, can you read it?
Yes.
NTS, right? You replace t there with NTS, right? Because when the delta function turns on, it just samples the value of anything next to it, right? So it means this whole thing becomes a summation from n equals minus infinity to infinity of x of n ts times e to the minus s times n ts. And now we're just about the point where we need to be. Now there's something I did here that was not quite right. This integration should have gone from 0 here, right? And that means this summation will start at 0. Agreed with that? Keep watching this last part. Now, what we end up doing is saying that this becomes the z transform. And we say x of z is equal to the summation of x of n equals 0 to infinity, of z to the minus n, where z becomes equal to e to the s ts. This is very interesting what I'm just showing you, because this gives you something that you didn't have before. Somebody knows this of that. What did I really do? I've eliminated the TS as something multiplying n, right? So now I'm assuming TS, but I'm sampling and storing the samples at 0, 1, 2, 3, 4, right? TS is a variable I have out. But I noticed one thing, that the actual Laplace transform becomes the z transform if I do this, if I put e of z equals that, or said another way, if I have the Laplace transform, just watch this. If we take the log of z here, right, and divide it by ts, that's equal to s, isn't it? You follow me? Now, why did I say this? Because this is something that, just like with the, remember with the Fourier transform, I showed you how if you have a continuous time Fourier transform pair, and you wanted the discrete time Fourier transform pair, you could get it by looking through your functions, and if you found a function that looked just like the frequency domain transform that you had with x of omega, you could get the time domain form by just looking at the Fourier transform pairing. You all follow me on that? We talked about that. Now, here's something. I know that e to the minus 2t u of t goes to simply 1 over 2 plus s, right? This is x of t, this is x of s. Go ahead.
Can z equal 0 in that statement? Because ln of 0 would be
Well,
infinity.
the problem is that you're gonna get into areas where there's limits on all these things, but if you had, if you have a z equals 0 here, then you have a minus infinity for s. Is
Right.
minus infinity a possible value? Well, theoretically, right? Because
We
it's
realize-
realizable now. Just telling you, that's it. Most of the time, z equals 0 is a non, what does that mean? That, you remember how you have the region of convergence? And I don't know of anything that includes, well, maybe there is something that includes z equals 0, but I'm not sure. I better be careful what I say. So we have this relationship. We have a time domain, frequency domain, right? If we want the z transform, we take s and replace it. We have 1 over 2 plus, and this would be natural log of z, there's an expansion here, over ts, and that would give us e to the minus 2, and now this would become nts times u of n. Now, there's an expansion on this that I'm going to get to later. Do y'all remember that there's an expansion on the natural log of z, so you can get into an approximate value? But what I'm really going to tell you is if you have anything where you want the z transform, inverse z transform for, you can use Laplace transform tables for it. I'll do more of that later, where it becomes applicable. So now we talked about the relationship between z and the continuous time Laplace transform, and how you can actually get get the z transform from the Laplace. Next. His book talks about all these things, and in his book, one of the things, in this chapter, he's going to dabble with all this stuff. And I'll tell you, the Fourier analysis that he does here, I'm going to talk about the functional form he has there, but I try to stick within the functional forms that I have. Let me mention about the DT, or the DFT next, and then we'll talk about FFT. So we've gone from continuous time, Fourier transform, and Laplace transform, right? Then we went to discrete time, Fourier transform, and we went to Z transforms, right? Right here. All these things required infinite integrations in time or infinite summations in n, right? That's non-realizable. But they give you enough information, you have a lot of analogies and pictures, you can actually see what's going to happen when you define it. Now the next thing we do is the DFT. It's the discrete Fourier transform. And it's from the DTFT. What they do now is truncate the actual series size. So now I get x of k, unlike x of omega, or x of capital omega, and that's going to be equal to a summation. And here, n is going to go from 1 to n minus 1. And now you're going to have x of n. All right, that's the series. And it's going to be e to the minus j. Then you have 2 pi, and you divide it by n. Now what that is the total number of points. So if you have, say, a 64 points for x of n, 64 samples, it would be 2 pi over 64 would be the angular increment. When you go through the entire series, you go through 2 pi radians. All right? Just think of it that way. It's this times n times k. All right? What it amounts to is this. We're summing on n, k is our index. K is like frequency. It's analogous to frequency. N is analogous to time, and that's the actual DFT. All right? The FFT is the DFT, and I'll just put it down here. The FFT, which is much quicker and faster algorithm, is the DFT, only now the summation will always be from n, actually that's 0.
Yeah.
N equals 0, and then it will be 2 to the, and they usually put 2 to the capital N minus 1. That means it's going to be 2 to the n points of x of n times e to the minus j 2 pi over n, over 2 to the n, pardon, 2 to the n to the mk power. Now, the fast Fourier transform has algorithms, they're Tukey, Cooley algorithm, and other faster ones that make it super efficient by using redundancy relationships. And they can do it. That's the reason for the FFT. There's a problem with FFT is if you don't have exactly 2 to the n points, you have to do zero padding. You have to add points until you get it to 2 to the n number of points. And zero padding does distort somewhat the information. We'll get to that in a bit. And you all had that in what class? I mentioned it in signals. Did you all have that? Did you have any other course? Signals and systems, I mentioned it, but I don't give you an exercise there. I mean, did anybody, you had somebody else, did they give you zero padding problems?
I believe so. In DSP,
Oh, not DSP though, I'm talking about signals and systems.
What is FFT again? You just did the FFT apply for it?
Well, what happens here is you have to have 2 to the n points here, all right? If you don't have 2 to the n points, you add zeros. In other words, if x of n here was 0, 0, or I mean, was say it's 1, comma, 5, da da da, all these values say 16, but there are only 12 samples. I need 2 to the n, so I have to zero pad out to 16 with zeros. I have to add zeros, so I have 2 to the n, and the algorithm doesn't work. Adding those zeros causes disinformation, it causes lack fidelity, lack accuracy. We're going to get to that too when we do the process. I mean, you have to be aware of what happens. Zero padding, there's all sorts of very clear statements on the amount of error you introduce with zero padding.
Didn't zero padding just introduce a lot of high frequency noise?
No. Zero padding won't do the high frequency. Well, it could. I take it back, it could. And see, there's parts of what I want to say. Normally, the FFT you don't use. You actually do an FFT shift in MATLAB, but you shift it down. And do you remember how we compared? You do, but unfortunately they don't. I got to show you this. You can take DFT or FFT information, and by adjusting with certain parameters, you can directly compare it to a Fourier transform. There's one provision though, the sampling rate on the data has to be so fast, much faster than a large change can happen in the value of the signal. But then we can directly compare FFT, DFT to actual Fourier transform pairing, and we'll do that just to get some perspective. And I gotta tell you this, the FFT right here by itself, if you just plot that, you're going to see a lot of disinformation. What you're going to see is something that will start at 0, this is with MATLAB, and it'll go to effectively 2 pi, but it's going to, the high frequency stuff we have to do an adjustment. That it's disinformation. What you have to do is shift it so it makes sense in terms of a Fourier transform. Do y'all have that? Did you have that in any other courses or not? Well, we're going to do that, I promise you. But I got to give you perspective before I can do it. Now, I used to go ahead and do some typical DFTs and FFTs, but I think you probably know how to do them fairly quickly. I don't know if you...
MATLAB.
Huh?
I just stick it in MATLAB.
Well, that's the easiest way. And frankly, nobody does it longhand. It's just to give you an idea of what you're doing when you do it long-handed. And there's all sorts of tricks to doing it. And I could show you a few, but I'm not sure it's worth it. You have to understand, though, this is now finite time. This is the stuff we use right here. Now, with Z-transform, I'm going to tell you another thing. The Z-transforms we truncate too. So when we have our x of z here, now we're going to have summations from n equals 0 to n minus 1 here, and it will be of x of n, and it will be z to the minus n here as such, but this is going to be a truncated z transform of that. And I don't know how much you remember about this, but most of the time when we're doing FFTs right here of things, what we take a look at is the impulse response of a system. We get x of n, and we use that. Do you know what FIR filters are? Finite impulse response. We're going to be doing that because FIR filters are used all the time. That's coming up, not right now. This is just perspective, because in this chapter, if you look, I just took you through the Fourier transform, and I'm going to do his async series here because this is one that we get all the time. And you should at least have perspective on this in terms of DTFT or DFT. So this is a very common radar signal they use, even though it's not realizable. They're gonna say something where I'm gonna have a signal at x of t here. This is the async signal. And I'm gonna say it's e to the plus j omega naught, and it's gonna be n times ts. And I think he uses n in the superscript here, but I gotta show. Yeah. He uses an f naught and 2 pi. I'm just using an omega naught. You can do this if you want to indicate that that is actually a scaled frequency. And he's going to say this is on for t, or for really n greater than or equal to 0, less than or equal to n minus 1. So he has these values, and this should be a value of n, by the way. Just realize the only thing that is a fast changing value that is limited in range from 0 to n minus 1, and it's 0 else. If you were to take a look at it in terms of just the real part of it, it's doing this. If we take the real part of x of n versus n here, it's going to be on, then off, and it's just one pulse of that width. Now he doesn't center it about 0, which would be the smart way to do it. He starts it at 0. So if I have this and I want the dTFT of it, then I'd say that my x of capital omega here would be equal to the summation from n equals 0 to n minus 1 of e to the j, and then it's going to be equal to omega naught hat minus omega here, minus capital omega, actually, times n. Follow me on what I did here. I had x of capital omega equal to the summation from n equals minus infinity to infinity e to the minus j n omega, right? That's the way it's stated, the transform. Y'all remember that form of that back in Signals and Systems? We used capital omega, correct, class? We didn't use an omega hat, we used capital omega. Now, if we take that and we replace x of n with this, it goes right in here. And the only thing I do is I add the exponents, and I put the omega 0 out in front, and I have a capital omega minus omega on the back side, all both times n, right? And I forgot the ts. There should be a ts right there. My bad. With me? Now that is the form of what? It looks like this, where I have a to the n from n equals 1 to n minus 1, doesn't it? And that's a typical geometric series. Do y'all remember me showing this? That geometric series goes to 1. It's a to this one, and that goes from 0, a to the 0 minus a to the plus 1, right? Over 1 minus a. Do y'all remember that? This is one that crops up over and over again. You got to get used to it. Now, what is a? We'll take a look at a. It's e to the j, right? Omega naught ts, omega naught hat ts, minus capital omega. Isn't that what my a is right there, that I have to the n power? Can y'all see it? Gotta make sure I want to make sure you see what I'm doing, because this, what he does is exactly identical to this, only he doesn't use capital omega, he uses that omega hat is. It's still a scaled omega. Now, when you get this, what does it become? Well, a to the 0 is 1, minus a to the n is really going to be what? E to the j quantity omega naught ts minus omega, right? And this is to the capital N power, or times n, over 1 minus e to the minus j, and it's omega naught ts, right here, minus omega, and that's what that is, isn't it? Hang with me on this one. I know it's getting a little, it may be boring, but you all see what I've done there? Now, how many see right here and here that we can factor out something so we can turn this into a sign and this into a sign. Y'all see that, class? Right? So when we do this, what do we factor out on top? This is really e to the 0, this is e to the j that, right? We add this superscript and this, which is 0, and divide by 2. So we take e to the j quantity omega naught times ts minus omega here, divide by 2, and we're left with, we're left with e to the minus j quantity omega naught ts minus omega over 2 plus e to the plus j omega naught ts minus omega over 2. And then downstairs, it's e to the, that should be a plus right there, guys. E to the j omega naught ts minus omega divided by 2. We have e to the minus j omega naught ts minus omega over 2 minus e to the plus j omega naught ts minus omega over 2. And all that says, when we do that, you see how this is going to turn into 2j times the sign of that argument? And there should be an n here. I'm so sorry I don't have that. There's an n there, and there's an n there. But there's not an n there. And now that'll become, and I'll put it over here, this becomes the async that he talks about in the book. So if you take a look at that, if I take these two phase terms, I'm going to just break them out by themselves. I want to leave them right here. That's just phase. I'll put that in later. Then I have the sync. I have really the sign of, now it's going to be as omega sts minus capital omega times n over 2 over the sign of omega s t sub s, or omega naught. Sorry, omega naught hat. That's omega naught. Yeah, it's just omega naught. You don't have to put a hat on. You can leave it like that, but it's a scale frequency. Minus omega over 2. And if that is my x now of omega, what they want is a plot of this. If it's versus omega, and I take the magnitude of x of omega right here, just try to realize this. This is my whole point to this thing. This looks like a safe function, but it's not at 0. It's positioned when omega is at omega naught ts, so it's skewed off axis. Here, this is going to be omega naught ts, and he shows us in the book on page, or figure 1410 on page 508. Please just realize what he's really showing you is, if we take the magnitude of that, he gives you an idea of if you have this is just one pulse. There's nothing wrong about this. You're taking one pulse, multiplying by just an exponential, single exponential, not a sine or a cosine, and you get this shift. And you know you're going to get a shift anyway. This is just basic modulation theorem, right? If you have 1 and it goes to 2 pi delta t, then if you take that one and multiply it by cosine, you shift everything out to the frequencies, plus and minus omega naught, whatever the cosine frequency is. That's what should happen. Now here's the thing. The longer that pulse gets, the narrower this gets. So as the pulse is more and more periods are added, suppose you add, instead, you take it as twice the length, this will start shrinking down. Eventually, as it goes to infinity, you have a single line there. That's the real take back from this stuff, all right? He wants you to make you see the longer something's on, the narrower the pulse is there, and he does that in page 509. You have to see that. Hang with me, guys. Windowing's next. It's 10:40, right? You got 5 minutes, right?
minutes.
3 minutes?
I'm pretty good.
I was gonna go through, some of the properties of Laplace transforms, then show it to Z transforms. But right now, I'm gonna just try to tie this up. I'm gonna do one thing, and then let's do this one problem that we've had that's wrong in the book. Guys, are most of you familiar with Python in here? I'm familiar with MATLAB. There's a MATLAB, it's for Python for people that know MATLAB, I've heard on the internet, and I'm gonna look at it. But I wanna write, I have a student who was just about to send in a paper. This is Luke, and everything he did is in Python. I'm gonna try to learn Python. I know Marcus, you sent me that, but the reason I'm telling you this is we're doing some digital signal processing stuff applied to radar very shortly. He's been doing it, I've been listening to him, trying to replicate it on MATLAB. MATLAB has more toolboxes in my opinion. It's easier to do certain things. Anyway, here's where I'm going with this. Once we finish this chapter, then we're gonna do real radar problems. All right? But we have to at least have an understanding of all these properties. So if you have, this is called a spatial number. It's really spatial number. Here, he uses K. K you can think of is analogous to beta. And beta is 2 pi over lambda. The difference with K, it's got a vector sense. So K is the wave number. But K is also something that has a vector sense. There's a KX, AX, typically KY, AY, and KZ, AZ. It's got a vector sense to it. Typically, the way you get this is simply this. If you've got a wave that's going in the A propagation direction, so this is the wave direction. And it's really a unit vector in the direction of the wave. Then, if you want the wave number K, you take simply beta, or 2 pi, over lambda, that's the free space wavelength, or the wavelength in the medium, and you simply multiply it by AP. Now, what are the units for beta or K? That's radians per meter, right? That's what it is, radians per meter. Well, this is how many radians per meter a wave changes in the X, Y, and Z direction. And it's very, very important to know that, because when you have waves incident on the ground, if the K vector is this way, what you want to do is see the actual wave number on the ground, which is going to be a reduced rate of that. You follow me on that? So you would take K vector and dot it with AX if you wanted the wave number on the ground, because that gives you things like undulations and rippling effects that you have to be aware of how fast it changes. Now, it has to do with scattering too. If you have diffuse scattering, it's not a problem, but if it's specular scattering, that number becomes very, very important. That's later on though. He talks about that. Then the problem that I gave you that was done wrong in a book. Did anybody catch this one? It's problem 3.
I didn't catch it.
Did y'all take a look at problem 3?
Yeah.
Problem 3 says this, and we're going to go on this one, Marcus. It says that I have, now listen to me carefully. He says I've got something that's got a lower frequency of 95 and an upper frequency, I think it's 125? Yeah. All right. And he says it's centered at 105, if you read this. Is that centered at 105?
Yes.
If it was 115, it would be right, but not 125. He meant to put 115 here. He meant to put that, because this would be what? If we take a look at, from here to here is 10, from here to here is 10, right? He had 125. Doesn't he have 125 in the book?
Yeah.
Right, that's an error on his part.
Well, couldn't it be centered where it's the highest? So it could
Not,
be
it's the
left
middle.
side?
It's got to be mid-band on these things, because these have to be symmetric. If this thing is based on any real signal, this has to be symmetric about the center point. Has to. All right, anytime you have a legitimate signal, an X of t, and you get X of omega, a legitimate real-life signal, then you get something where the magnitude is evenly distributed about 0.
Not just a single sideband or
That's
outside.
not, no, that's not X of t. That's a modified form. You're suppressing part of the actual transmit. I'm talking about any real waveform. But for this waveform, he has something like this. I'm just going to leave it at 115, center frequency 105. Now he says he wants to sample it, and he wants to have this thing, one of the samples centered at 0, and he doesn't want any overlap on the sidebands. Now you can think about this. If I sample this at 20 megahertz, if this is a 105 megahertz, then every 20 megahertz it would step and repeat. That would be on the hairy edge of it, right? Do y'all agree with that? If it's at 115. That would get a sample here, and it would work. But now you've got these two butted up against each other. So you would want to sample it at something higher than this. He says 35 megahertz would be the sampling frequency. 35 megahertz would work if it was at 125. But then the center frequency is different. Trust me on this problem, the solution is wrong on this one. Just be aware that if you want to sample replicas and then extract information, you have to make sure that you sample such that the center of that thing that is out there, if you take a look at the center frequency where the modulation is about, when you sample it, you have to have a sample line right on the 0 point. And you have to give enough rooms for the sidebands not to overlap. That's critical when you do sampling for down. To get rid of an IF mixer, anything like that, you can just sample at a frequency and you can get it down to baseband and then you can put a low pass filter through it. But you can't have the sidebands overlap. And you can't have it something where, suppose I sample it like, not 25, but 20, or not 20, but 22 megahertz. Then I get every 22 megahertz, and then it's not centered. Do y'all follow me on this? That's critically bad. You've got to have the sample. When you sample that thing, one of these repetitive things has to be centered here and the same amount above and beyond the center frequency.
Could they touch? Could they be perfectly, or do you have to leave some level of gap?
You never want to even think about that. You want to put a margin for error so that you're going to get a guard band literally of at least 10%.
Wait, so
Okay,
10%
that's what I was-
would be sampling at 22 megahertz then, right?
No. Think about where it's centered. Here, let me just show you this. If I sampled a signal like this, just work with me. Let's say it's 100, just 100 megahertz, right? And it's got a bandwidth, so it goes from 90 to 110. Just work with me, all right? All right. Let's sample that at 20 megahertz. At 20 megahertz, every 20 megahertz it repeats, right?
Got it.
All right.
Yeah.
Now, if it's at 22, does it ever hit 0? No, it's skewed, right? Now you've got more on one side than the other, and that will not demodulate well. It won't. Trust me on that. But this is where you can use sampling to get rid of an IF mixer or really to mix down stage.
You can sample at 40.
You could.
Okay.
All right. You have to make sure one of the samples lands here.
Right, yeah.
All right, but as long as it lands at 0, follow me? Then you can do all sorts of stuff. By the way, this is really the essence of a lot of the stuff that they're doing with all digital radar and software-defined radio. Is using sampling, and you know the whole deal with software-defined radio is what? You have no IFs, you have no mixers, you have no intermediate frequency, no pass, none of that stuff. So you get rid of all that equipment. You've done a software-defined radio lab, haven't you?
No.
I took it.
Don't they have that anymore?
I didn't
No,
have it.
there were
It's
some
not-
nice students that signed up for it. I
it's
took it.
optional.
Oh, that's such a valuable course.
I'm actually, what I'm doing is I'm incorporating some software-defined radio into the wireless design lab, but you have to be a
All
wireless.
right, let me
manager.
just tell you this. Here's the big deal, and you can go, and I hope you have a great week.